So let's go straight into naming this compound without wasting time. So I gave just there are a lot of rules. I'm not going to list them. So why I'm just giving you those rules, I want you to write down. But the first thing you should know is that when you want to start naming from the positive side. If there is a counter ion, now don't forget you should know the meaning of counter ion. There's a counter ion. This is a counter ion here. Here, this is a counter ion. That okay? Because in some cases, I can decide not to. We can have a complex without a counter ion. Is that okay? For example, we can have something like this. Have something like this. Have something like this. Now, this is an ordinary complex ion. You can see that this does not have a counter ion. Is that okay? But in case you have a counter ion, because that means this all of this place is positive, the all of this place is negative. Here is positive. Here is negative. Is that okay? Is that okay? So don't forget, I've given you some clue, some informations about them. These are counter ions, and these are counter ions. Then inside the square brackets, we have our transition metals, which is positive, our ligands, which can be negative or neutral. Our transition metal is known as Lewis. We call it Lewis acid, and our um, ligand is known as Lewis base because they supply, they donate their lone pair of electron towards the transition metals. Is that okay? So that's why sometimes you can put the point down that our transition metal that is positive here is a Lewis acid. Our ligands, which can be negative or neutral, is a Lewis base because they donate their electron towards this center. So they are always surrounding it. So let's start naming. So when you're naming, you name from the positive side. So where's the positive side? When I mean positive side, I means if there's a counter ion. Do we have counter ion in the case of this compound like this? Yes, this is the counter ion, which is potassium. So I'll start with potassium. So I'll start with potassium. Is that clear? Potassium. So I'm starting with potassium. Then immediately you are done with the counter ion, you go straight into your square bracket. But for example, where this does not have a counter ion, you just go inside your square bracket. Now, in the square bracket, start naming with the ligand. So when we are inside the square bracket, we start with the ligands. So I'm done with the positive. So when you have a counter ion like this, you start with the positive side, potassium. Then when you are done, you go straight to your square bracket. Inside the square bracket, we have transition metal, we have ligands. You start naming first with the ligand. Start naming first with the word ligand. Now we have different ligands and the way we call them. Now the number of cyano here, cyano is, we have 6 cyano here. How many cyano? We have 6. So we have some Greek names we use. We have 2 cyano, you say it is di. If you have 3, you say it is tri. So if we have 3 tri, tetra, you understand? So when we have 6, it should be hexa. So don't forget. Now, you know that cyano is a negative ligands. So we have a name the way we call them. Those negative ligands, their names end with O. So the cyanide becomes cyano. Chlorine is negative. So chlorine is also a ligand, a negative ligand. So because it's a negative ligand, it ends with O. So put that point down. It ends with O. So we have chloro, cyano, OH minus, hydroxo, uh, Br minus, bromo, oxalate becomes oxalate too. So these are examples of them. You can snap them. So bromide is negative ligands, bromo, chloro, cyano, fluoro. Consider everything is ending with O. Now this is because they are all negative anionic ligands. So but we have some ligands that are neutral, like I said. And don't forget, ligands are Lewis base. We have some neutral guys like ammonia is neutral, does not have a charge. We call it amine. Water does not have a charge. We call it aqua. Carbon monoxide without a charge, carbonyl. Then ethylene diamine. which sometimes we use En, is ethylene diimine. So I want you to know that. Note that. Now, let's go back. So once I've called the counter ion, which is potassium, and I move straight to my square bracket, which is the negative side here. So I called first the ligand. So how many cyano do we have here? We have 6. So we have 6. That will be what? Hexa. Potassium hexa without space. Potassium hexa cyano. So who is the cyano? This is the cyano. Now, cyano, the next, once I'm done with the ligands, then I'm going straight to the central metals, which is the transition metal. Now, how do I call transition metal? In some cases, our transition metal, the name ending is ATE. And in some cases, we call back the name without putting ATE. For example, I can say cobalt or cobaltate. I can say ferrous or ferrite. I can say chromium or chromate. So there are rules to it. Now, if your complex, that's it. If your complex ion is a negative complex ion, what do I mean by that? That means this square bracket, it is negative. You can see it is a minus. If it is a negative square bracket, because our counter ion is positive, that means this square bracket is negative. If it is a negative square bracket, if it is a negative square bracket, then the name of the transition metal will be ending with ATE. Cobalt will be called cobaltate. Chromium will become called chromate. Platinum, platinate, like that. Then ferrous, which is iron, will be called ferrite. So in the case here, our complex here, the complex ion here is towards the negative. So we are going to have hexacyano. Then what will be the next thing? Ferrite, not ferrous, because it's towards the negative side. Ferrite, thank you. Then to end it all, we are going to calculate the oxidation state of Fe. Now that leads us to how to, if a question says what is the oxidation state of a complex? Oxidation state of a complex is very, very simple. The oxidation state of a complex, you are looking for the charge of Fe, and I can do that real quick for you. So all we do is that it's either you take it as a whole, or you break it, then you take it as this. Any one of them is okay. So if I'm taking it as a whole, you know that this is a compound. That means K3, when we have Fe, then we have Cn, then we have 6. If I'm taking it as a whole like this, I'll say everything, the whole charge is equivalent to 0. I believe you know how to calculate oxidation state. But if I'm using it like this, I'll say everything is equals to minus 3. Do you understand? So I'm looking for the oxidation state of Fe. So you know that the oxidation state of potassium is +1. That's 1 multiplied by 3. Plus Fe is what we are looking for. Plus our cyanide Cn is -1, but we have 6 here. That will be what? -1 multiplied by 6. Then we have everything equals to 0. So we have 3 plus Fe minus 6 equals 0. So we have Fe to be equals to 6 minus 3, which is +3. So I can come and say potassium hexacyanoferrite oxidation state of the complex, which is the oxidation state of the Fe, is 3. So then we put 3 in Roman numeral, capital letter. So we have potassium hexacyanoferrite 3. I think that is clear. So I think we can move straight to the next one. And what's the next one? Let's look at this guy. We want to name this guy. Now, if I'm to name it this way, without the potassium, the answer will just be what? Without the potassium, I'll say hexacyano is still ferrite. Then it's still 3, because I'm naming it like this. But instead of potassium, we've removed, there's no potassium. In the case where we have this, there's no potassium. So because there's no potassium, then you say what? Ions. So hexacyanoferrate, 3 ions, this is it. Then potassium hexacyanoferrate, 3 without ions, this is it. I think that is clear. So let's look at this one. So if you take a look at this one, where's our positive side? Start naming from the positive side if there's a counter ion. We have a counter ion. The counter ion is negative. So, and anytime we are naming from the positive side, meaning I'm starting my naming from this side. So, and this side, don't forget, it means that our complex is positive. We are starting our naming from here. I will not call chlorine first. I have to call everything here first before touching chlorine. Here I called potassium before going here because this is positive. So here I'm calling this guy first before going to my chlorine. So very simple. Inside the square bracket, who do we call first? Inside our square bracket, we start calling the ligands first. Now, how many types of ligands we have here? We have different. We have what? We have H2O, which is aqua. H2O is what? Aqua. Then we have we have chlorine here, which is chloro. So these are the two ligands, and this is the counter ion. So we are starting from this guy. So we start with what? How many water molecules? How many water? We have 4 of it. So 4 is tetra. I think I taught you that. So we say tetra. Now, don't forget that this is aqua, and this ligands here is chloro. Now, aqua and chloro, which should I call first in alphabetical order? A comes before C. So I'll say tetra aqua. I think that is tetra aqua or aquo. You can see it aqua, you can see it as aquo. No problem. Tetra aqua. Then after tetra aqua, then the next one is what? Chloro. Tetra aqua. Chloro. Now, what happened to our chloro? Our chloro is 2. 2 chloro. Is that okay? 2 chloro. So tetra aqua. Then we have what? Dichloro. So I've mentioned the two ligands. Don't forget, I'm starting my naming with the one in the square bracket because the whole of the square bracket is in the positive side. You notice I'm not starting with chlorine. Yeah, I started with potassium because potassium is at the positive side. So tetra aqua dichloro. Can I continue? Dichloro. Then after mentioning these two, you are going to your transition metal. Now, our transition metal here, I want to ask a question. Will it be called chromates or will it be called chromium? For those who understand what I said. I call my ferrite, and I gave reason. Will our chromium here be chromium or chromates? Now, it's going to be chromium because the whole of this square bracket is at the positive side, meaning our complex here is a positive complex. Our complex here is a negative complex. So that is why it ends with ATE. A positive complex ion does the transition metal we don't end with ATE. So tetra aqua chloro, then chromium. Then the next thing is to put the charge. I mean the oxidation state. So we can also calculate the oxidation state of everything. I taught you how to do that. So we are looking for the oxidation state of chromium. That will be chromium plus. What's the oxidation state of water? Water is 0. Does not have a charge. 0 times 4 plus chlorine is -1, and we have 2 of it. That's -1 times 2. Then plus this other one. So we are doing everything together. So don't forget that we have to equate everything to 0 since we are taking everything, unless you break it. So plus, then this chlorine here is what? -1. Everything equals to 0 because it's a compound, it's a coordination compound. When you break it, then it becomes ion. So from here we have Cr, then we have plus 0. So plus, this is -1 times 2 plus 0 minus 2 minus 1 equals 0. So we have Cr to be equals to 2 plus 1, which is what? 3. So the guy is plus 3. So we have it as plus 3. So I can come tetra aqua chlorodichromium, tetra aqua dichlorochromium 3. Now I'm done with the whole of this, so I can move to this guy. Then, you know, sodium chloride. So this becomes chloride. So this is chloride. So tetra aqua dichlorochromium 3 chloride. I think that is very, very clear. Now, to name this last one, to be easier for you, you have to break this complex into the positive and negative complex ion. Though I'm still going to talk about, there are some complex compounds, I mean, that, because I told you that this complex, this square bracket can either be positive. I mean, the whole square bracket can either be positive. Yeah, the square bracket is positive. I mean, yeah. Then yeah, the square bracket is negative. Then there are some cases, rare cases, whereby the square bracket will not have any charge. Yeah, the square bracket is positive, yeah, it's negative. We have instances where the square bracket is going to be uh, neutral. And most time when the square bracket is neutral, for example, like this guy, PT, NH, NH3, 2, F2. Now, this is one example. Now, this is where you have it. Now, this guy is not ion, does not have counter ion. Can you see that there's no counter ion? It's just like this. And it is not positive, it is not negative, it is neutral. In most cases, the way they write it, since it is not having positive or negative and there's no counter ion, you always see it without the square bracket. So you see it this way, so don't be confused. You see it this way. You see it this way without the square bracket. So it is a complex. This is the um, transition metal. Then this is the ligands. So we are still going to talk about it, and that is why you should check the introduction of this um, complex so that you can understand better. So let's go straight to this naming. Very easy. We go straight to this naming. We break it into the positive and negative side. You know that this is positive, this is negative, and we already know that this guy is +3. I think I told you. That's why you should check the beginning of this video. So we have CO, we have NH3, and this one becomes 3 plus. Then this one is, I'm breaking it into two. CR, CN, then 6. This is 3 minus. So to name it will be easier one way or the other, but we can put them together. So we start, this is the positive side, this is the negative side. So where do we always start naming from? From the positive side, meaning I have to start with this square bracket. Now inside this square bracket, who will I start with? I will start with the ligands, then to the transition metal, the ligands to the transition metal. So I think that is clear. So what do we have here? 6. Ammonia is going to be called what? Amine. Ammonia is going to be called what? Amines. Amine. Yeah, I think I told you. Ammonia is amine. So ammonia is amine. Ammonia is amine. So then we are going to have hexaamine, 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 then cobalt. Hexaamine, cobalt. Now, take a look at it. Hexaamine, cobalt. Now, I'm not saying cobaltate because this side is the positive side. I think that is clear. Hexaamine, cobalt. Now, I need to look for the oxidation state of cobalt here, which is very, very simple. Since it's 3 plus, I can just say cobalt plus ammonia does not have a charge. That's 0 times 6 equals everything plus 3. So from here, I can say cobalt equals +3. So cobalt 3, and I continue because there are 2. So I'm done with this side, then I have to continue with this side. Now on this side, I'll still have to start with the ligands. What ligands we have there? We have imine cobalt 3. Are you following? Then this becomes what? Hexacyano. Hexacyano. Are you still following? Hexacyano. Then I can call this our chromium here. Will it be chromium or chromate? It will be chromate because this side is the negative side of this side is positive side. So this is coming chromates. Then we can calculate the oxidation state of this guy also, which is Cr plus this guy is minus 3. I mean minus 1. Cn is minus 1 times 6 equals minus 3. Everything is minus 3. So from here we can have that chromium equals, that's going to be minus 6. Those 6 minus 3, we have 3. So we have 3. So simple. Now I want you to note this compound because there is a rule I want to mention so that you add to what you have already. Now if you look at this compound, this is this O complex. That means our square bracket, this is still the same thing as this. They are the same thing. Now this part is the positive. The whole of this is positive. Then this is our counter ion, which is negative. So you should know that. Then and that thing I want you to know here is that okay, I'm concerned about the ligand. Now this is the ligand. This ligand is ethylene diamine. Now if you want to name this compound, you should know we know that this ethylene diamine is the abbreviated to EN. Anytime you see EN, it's still the same thing as ethylene diamine. Now if you want to name this the way we normally name without wasting time, this side is our positive side. We start naming with the ligand, so that will be tri. Now we don't use the word tri. This is three of this guy. I mean 3 of ethylene diamine. So if we have 3 of ethylene diamine, we should say triethylene diamine. But because the ethylene diamine itself is having a Greek word already, and where is that Greek one? Di. That guy is already having di. He's having a Greek word, di. So any ligand that is already having a Greek word included in it, I mean a Greek word used for number. Ethylene di means 2. So we don't want to say triethylene di again. So in this case, not to cause confusion, we'll not be using tri, di or tetra. Anytime your ligand already have a Greek name for number, ethylene diamine has a Greek name, di in it, which is for number. So in that case, our we will not be using the word di again. For 2, we'll be using bis. For 3, we'll be using tris. For 4, we'll be using tetrakis. So in the case of this guy, his name is ethylene diamine. He's having a Greek name for number already. So if I want to name it, I'll say tris, not try. And I told you the reason because of the name. Tris ethylene without space. So there won't be space. Ethylene. Ethylene diamine, triacetylene diamine. I think that's what I just want you to note. Then what will you be calling this one? Will it be cobalt or cobaltate? You should have known by now. Cobalt or cobaltate. It will be called what? A cobalt because it's at the positive side. Cobalt. Are you following? Cobalt. Then the next thing is to what? To give it its the oxidation number of this guy here. I've calculated it is going to be plus 3. You can also do 3. Then we have our counter-ion. What's our counter-ion? The counter-ion is chlorine. This chlorine is not a ligand, it's a counter-ion, so just say chloride. As simple as that. So what's the lesson here? The lesson is that if the Greek name is already having, what do you call it? I mean, the ligand is already having the Greek name for number like di, this di, I mean. So ensure you change the numbering to 2 should be bis instead of di, 3 should be thrice instead of tri, 4 should be tetracase. So normally that's why I'm using thrice, not tri. So that's what I want you to note. Then let's talk about this last compound. I said something about this compound. I said, if you see, I use a square bracket and there's no counter ion and there's no charge on it. So these are complexes that doesn't have charge. I mean, it's not, it doesn't have a counter ion beside it. It is not positive, it is not negative. So it is neutral. So most time they don't use a square bracket when it is neutral. You see it this way. When you see it this way, this is the ligand, so that you not be confused in case you see question like this. Sorry, this is the transition metal. This is the what's this? This is the ligand, and this is also the ligand. Is that okay? So you won't see it with the square. You see, they will remove the square bracket. Immediately you remove the square bracket and write like this for you. They are indicating that it is a neutral complex. So how do we name the same way? Since it's a neutral complex, you just say we start naming from the ligand. So this is the ligand. So that's diamine, diamine, diamine. This is diamine. Then what else again? Difluoro. Now, will I call it platinum or platinate? Since it's neutral, since it's not positive, no, it's still, you call it back the name platinum. Then calculate the oxidation state of PT here. The oxidation state will give us, because you equate everything to 0. Since there's no charge, the answer will be, if you calculate it, should give you a +2. Should give you a +2. So just say, ensure that there's no gap between everything. So platinum 2. So what do we learn here? In some cases, your complex can be positive, your complex can be negative, and your complex might not have any charge. Is that okay? Now, if your complex like this guy is neutral, is neutral, you can see that it's not even having a counter ion. For this one now, look at it. This is a complex compound, but we know that this guy is positive. How do we know? Because it has a counter ion that is negative. I think that is clear. This one, we know that this complex is positive because that's a counter ion negative. We know that this complex ion is negative because counter ion is positive, and like that. So I'm going to give you questions to solve. I'm going to drop a question. You are going to solve those questions. I'm going to attach the question immediately on this. So please try all the questions. Give me the answer in the comment section. And we are going to move in straight to ensure you check the introduction. Check the introduction to complex, the video I make. Then from there, I'm going to go to how to get the magnetic properties. From there, we'll look at how to know those who are colored ion. Thank you.